Well, it's good to be here with you today, John. 5 years from the anniversary of coining NISQ. In case there's anyone who doesn't know, NISQ stands for Noisy Intermediate Scale Quantum, with computers sometimes appended. Happy anniversary. In the next few years, we are going to see quantum computers with thousands of qubits and gate errors below 10 to the minus 3. That's great, it's a solid improvement, but I think a question that a lot of people have is, it's very far off from the millions of qubits with the fault-tolerant state. And are we still in the NISQ era? Are we going to be in the NISQ era? Are we going to be stuck there forever? Not to blame you for it, but where are we going?
Well, thanks for the question. Before I answer it, I just want to remark, for the sake of full disclosure, that Mad said, and I hope it's true, that I don't have a dog in the fight, but I do have a affiliation with a company. I'm an Amazon scholar, so I'm connected with the Center for Quantum Computing that Amazon has established at Caltech, where I work. Are we still in the NISQ era? Indeed we are. I think the distinction that NISQ draws is machines that are not error-corrected, that aren't able to make use of the ideas of quantum error-correcting codes and fault-tolerant quantum computing. That's why N is in the acronym, because they're noisy, and the noise is a real limitation on what they can do. Are we going to be stuck there forever? No, I don't think so. But we do expect that to run the applications which are likely to deliver broadly impactful practical applications, we're going to need much, much lower error rates per gate, and that means we're going to have to do quantum error correction. And as you said, that's a big leap, because it's going to mean many more physical qubits. So what I was saying 5 years ago is that we have to keep our eye on that goal of reaching fault-tolerant quantum computing, which we really can scale up to large circuits, but at the same time, let's see what we can do with the machines that we have.
Yeah. Well, so that's a natural segue. Let's talk about error-correcting codes. Can you tell us what you think are some of the most promising steps being taken in that direction these days?
Right. Well, we would like to see convincing demonstrations that quantum error correction really works. What do we need to see? Well, quantum error correction entails, many times in succession, measuring the error syndromes, which tell us about the errors that need to be corrected. So we need the ability to perform many rounds of syndrome measurement. And what we would like to see is that at the size of the code, as the number of physical qubits in the code block increases, the error rates at the logical level decrease very sharply. And we're not there yet. There have been promising developments in the last year or so in that direction. The Quantinuum group, using an ion trap processor, did perform logical operations on 2 code blocks, a logical C-NOT gate. We saw from the Google group that they looked at codes of 2 different sizes, code on a 3x3 lattice and 5x5 lattice. The former can correct a single error in that set of qubits. The latter can correct 2 errors. So once the gate error rates are low enough, we should see a big improvement when we go from 3x3 to 5x5 and onward. And we're not quite there yet. And the issue is just that the 2-qubit gate error rates are still too high. They have to be better by a factor of a few. And when that happens, I think it'll be kind of a milestone. We'll see quantum error correction starting to kick in. And what we really want to see is improved gate error rates from using quantum error correction.
Yeah. On the theoretical side, I know that some people have disparaged the 2D surface area codes, and they've said these are not the future because they're just not efficient enough. Do you have an opinion about that? Do you feel like there is a low density parity check code that you think is the one?
I think the surface code is the near-term future of quantum error correction. It has some notable advantages. It requires only geometrically local processing on a two-dimensional layout, like for qubits, on a chip. And it tolerates relatively high gate error rates. Mm-hmm. And that's the big issue now, that we need to have gate error rates which are below the so-called threshold, the level of noise that code can tolerate, and we don't have a better candidate. There have been impressive theoretical developments in the past year toward more efficient codes, as you were suggesting, quantum low-density parity check codes, which have some of the advantages of the surface code. In particular, that in order to measure error syndromes, you only have to talk to a few qubits in a very large code block. The advantage is the codes are more efficient in two senses. They can encode more protected qubits per physical qubit than the surface code can, and also the distance of the code, which is a measure of its error-correcting capability, grows more rapidly with the number of physical qubits. How practical those codes will be is still an open question. They do seem to require lower gate error rates for their error-correcting capability to kick in. And actually, we still have a lot to learn about how to decode those codes efficiently and how to do logical processing with them. That's an active and really interesting research area right now.
Yeah, and I don't mean to bring up something impractical, but I know that there's been interest in error codes in black hole research and condensed matter systems. Can you talk about a little bit of that, and then we'll get back to the practical stuff?
I'm delighted by the question. Yeah, it's a quite active research area to connect ideas from quantum information such as entanglement and quantum error correcting codes, computational complexity, to areas of basic physics, including quantum gravity and condensed matter. In the case of quantum gravity, I think we increasingly have reason to believe on theoretical grounds that space-time itself is not really fundamental, but it's a kind of emergent property of highly entangled systems. And I think that's really interesting because I believe that eventually we will make use of quantum technology, quantum computers, and quantum simulators to understand better the quantum physics of space-time itself. And what seems to be the case is that in order to understand that emergence of geometry from a highly entangled many-particle system, the idea of quantum error correction is central, and we're still trying to understand that better.
Sounds good. Back in the direction of more practical things, there's been a lot of interesting back and forth in the sort of quantum advantage, quantum supremacy experiments, most recently a paper by Haranov et al. To your mind, where do things stand? Who has the advantage, classical systems or quantum systems?
Well, as far as the paper you referred to, it's a theoretical paper about the asymptotics of how hard it is to simulate a quantum system using simulate a quantum circuit that's noisy using classical computing. The idea of quantum computational supremacy was never really about asymptotics. In the case where we're using noisy quantum devices, if you wait long enough, the system just completely randomizes and simulating it becomes easy. It's always been about kind of an intermediate regime where we think it's hard to simulate an ideal quantum computer classically, but the noise is low enough so we can get into the regime where that's hard to do. Now, part of what the quest for quantum computational complexity has resulted in is better classical simulation methods, which is a very good thing. And the current status is that the gap between how long it takes to run a random quantum circuit on a superconducting device and how long it takes to simulate it classically, that's narrowed a lot. The fundamentals haven't changed, which is as you increase the number of qubits, the classical complexity cost increases exponentially. So with somewhat larger devices, that gap will open up wide again.
Sure. Now, you've been working on sort of figuring out where we're going to have quantum advantage. You've written papers about machine learning and quantum chemistry. It seems like generic quantum advantage is hard to prove, but that there are probably a lot of sort of specific problems which will benefit from a speed up. Is that right?
General quantum advantage? Well, we don't think that quantum computers can dramatically speed up everything. Naturally, there's been a lot of interest in applications of quantum computing to optimization problems, and that would be broadly useful.
I meant generic in terms of machine learning or quantum chemistry.
Quantum chemistry, machine learning. Well, I think as far as, based on our current understanding, where we expect practical impact in the long run from quantum computing, one of the main targets is applications to quantum chemistry and quantum materials. That's where the quantum computer has a natural advantage in understanding how highly entangled, very complex quantum systems behave. And a lot of effort has gone into costing some of those algorithms. And as far as we currently understand, we'll need fault-tolerant quantum computing. We'll need much better error rates per gate to run some of those applications. But one thing I think is worthy of note is that the machines we have now are already scientifically interesting. You know, they're enabling us to explore the properties of highly entangled systems in regimes where we never had experimental access before. And there's a type of quantum advantage there. For example, there was a recent experiment studying the properties of the Hubbard model, which is a mathematical model of a kind of caricature of a material like the copper oxide planes in high temperature superconductors.
Sure, a lattice with spins.
Yeah, and it's a hard system to simulate classically, but there have been experiments with atoms trapped in optical lattices with 100 particles where you can study the dynamics, how the system, if we suddenly change it, evolves in time. Seems to be hard to do classically. Experimentally, interesting results are being obtained. There are other examples like that. So scientifically, it's a very interesting time. What does that mean for the attendees of Quantum to Business? Well, I think it means the scientific advances will continue, and that's going to set the stage for applications in the future. So it's something we should all encourage.
Yeah, and I think something that other people have mentioned, you've, I think, written about this yourself, is that the speedups don't have to be exponential to be valuable. You can still have some kind of quadratic speedup that matters a lot.
Well, that's fair, but we'd really like exponential speedups, or at least super polynomial speedups, or better than quadratic speedups. Because in the case of a quadratic speedup, where we would see quantum optimization kick in as much larger instances, and we'll need much larger fault-tolerant machines before that's possible.
Does that suggest, an importance for error mitigation in the near-term NISQ future?
Sure, we should get as much juice as we can out of the technology we have now. Because quantum error correction has such a high overhead cost, it can't be, well, it doesn't even work yet, but it's not going to be used in running algorithms with quantum advantage for a while yet. To extend the capability of the noisy machines we have now, there are other techniques short of full-blown quantum error correction, which can extend the reach. And one of them is probabilistic error cancellation, where one runs a number of different circuits and then adds them together with appropriate weights. For that to work, you have to have a very good characterization of the noise, but we're getting better at characterizing noise. It still scales exponentially, so the resources you need, the number of times you need to run the computation as you increase the circuit size, increases exponentially, so there's a limit to how far methods like that will be able to go. But I think they will be helpful, in the next few years in reaching to larger circuit sizes.
Sure. I think with the pace of quantum news, it's impossible to keep up with every development. But is there anything that you think has sort of been like forgotten, or has it sort of slipped through that you'd like to point to as promising? Remind us that it's happened.
Okay, well, I'll remind you that it recently became possible to access on the cloud a neutral atom system that QEra has produced. It's a 256 qubit device, and I don't mean to emphasize that particular device, but it is a hardware approach, which I think 5 years ago, the first time there was a Q2B, wasn't so much on the radar screen. But now, at least scientifically, looks very promising. It's a highly programmable device, which enables us to explore the physics. It's an analog quantum computer of many entangled particles, and I think we're going to see scientific advances in the next few years resulting from that kind of technology.
Okay. We have a few minutes left. I think people wanted us to turn it to the audience because I'm sure people have questions for John. I think there are microphones. Yeah.
Hi, John. My name is Dikshant. I worked under one of your PhD students, Hui Kun, in CQT in Singapore. And as a joke, I tell my friends that NISQ is synonymous to Q-pop, and Q-pop as in quantumly premature and overhyped period. And my question to you is really about navigating the hype that is out there today. So just as a couple of examples to tell you, we saw stock price of one of the companies plummet because of the radical promises they made. I don't want to give out names. Another example is really one of your good friends, Scott Aronson, had to write an email to New York Times because they basically said that scientists discovered a small wormhole using quantum computer and things like these. So my question to you is really, what can we as a community and someone as influential as you can do to really navigate the overhype that is out there today and be completely realistic about the potential of quantum computing in today's era? Thank you.
No, not quite. Could you understand the...
Yeah, so the question was, how do we navigate the hype, especially considering things like news about a wormhole on a quantum computer?
Well, I can say what I try to do, which is to, when I have the opportunity, to say what I really think the situation is. The hype is to be expected. There's a lot of excitement about the field. The reason I come to Q2B for 6 years in a row is because I think it's an opportunity to say that while quantum technology is going to be broadly impactful eventually, it's going to take a lot of time and effort and investment to get there. In the case of this recent story about wormholes in the New York Times and other publications, I guess it was kind of irresistible because it checked a lot of boxes, quantum computing and quantum gravity and wormholes and so on. I can put that in the context of what I said earlier about exploring quantum gravity with quantum devices. I think that's something that will be scientifically informative in the long run. Of course, we're not there yet, as in other arenas of quantum simulation. That was an experiment with 9 qubits in a quantum device, so of course it couldn't teach us anything we couldn't find out from a classical computer. But there was an interesting scientific observation at the core of that paper. They took a toy model of quantum gravity and used classical machine learning to make it much simpler so that it could be simulated on a quantum device. And that's an example of the kinds of things we hope in the future will enable us to explore with the quantum technology we have, quantum phenomena that we didn't have access to before.
I think there's a...
Yeah, I wanted to ask if you, what your thoughts are on whether analog algorithms have any chance of showing a quantum advantage before you deal with error correction.
Well, in a way, I've already addressed that, I think. I think that's happening now, as in this simulation of the Hubbard model. That wasn't a circuit-based quantum device. It was really an analog quantum computer. In the case of the neutral atom systems in tweezers, we can study dynamical phenomena involving hundreds of qubits now, which are hard to simulate. And there have already been some surprises which have caused the theorists to reconsider some of that physics. Another thing that it's more on the circuit-based side, but maybe is worth mentioning in the context of potential quantum advantage that we have access to now, is there was a recent experiment with an ion trap device using 26 entangled ions to improve sensing. And it was a kind of variational algorithm, actually, in which they had circuits with free parameters and optimize those parameters to get the best possible sensitivity in a sensing context. And, that's the kind of thing we can do now. People have been interested in using entanglement to improve quantum metrology for a couple of decades. But now we have technology where using either analog devices or quantum circuits, we can explore that in a scientifically meaningful way. And like I said, I think as we advance the science, that's eventually going to open new applications that are of broader interest.
Yeah. I think there was somebody in the front who had a mic, and maybe we have time for one more question.
Appreciate you taking the time. If you look at where we're going here, it's really, I think of it as 3 vectors all coming together: error correction, algorithmic efficiencies, and hardware. If you just looking at those 3 at a high level, who's in the lead to getting to where we need to go?
Which is the most important of the 3? Is that
Yeah, I think
the
that was the question.
Well, obviously they're all important. There are huge engineering challenges at realizing the kind of large systems that we're going to need, which don't really have to do with the quantum processor itself. Controlling it, the software we'll need, and the control electronics and so on, all those things are challenging. But what I personally would most like to see is much better qubits, in the sense of much lower physical error rates, because that's going to open up both further applications of the NIST technology and also lower the cost of quantum error correction, which is going to bring us closer to scalable quantum computing. So let's everybody get to work on that.
Better qubits. You heard it here.